So, all right, namaste and welcome to lecture 11. Okay, so before we begin, let me, allow you all to ask questions with regards to the topics that we discussed in the previous class. Let me know if you have any questions. Please raise your hand if you do have. All right. So I don't see any raised hands. So let's do a quick recap of what we did last time. Okay, so if you remember, last time we sort of looked at the matrix representation of these boundary operators, and then we asked, using these matrix representations, can we compute the Betti numbers? Okay, so we said yes, we can reduce these matrices to these row reduced echelon form. Okay, look at their the column rank as well as rank of the null space. Okay, and use the dimensions of these spaces, and then indeed compute the Betti number. Right, so thereafter we started discussing this Mayer-Vittoris theorem. So of course I did not state the Mayer-Vittoris theorem last time. So I mean, it wouldn't have been possible to state it because there are too many technical terms in the statement of the theorem, right? So we sort of started giving a discussing the motivation for this Mayer-Vittoris theorem. So the idea was that, let's say we have a complicated topological space X. So complicated here means that for some reason we cannot compute directly, or it's a bit hard to compute directly the homology spaces associated with X. But let's say X has this decomposition K1 union K2, and somehow let's say K1 and K2 are such that their homology spaces can be computed in some way. So then this Mayer-Vittoris theorem, as you will see later, okay, connects the or relates the homology space of X with that of the homology spaces of K1 and K2. Right. So this is roughly the motivation for this Mayer-Vittoris theorem. And we said that we couldn't state it because there were some technical terms involved, and we started discussing those technical terms. Right. I think in the previous lecture, I sort of used the phrase Mayer-Vittoris sequence. I think my usage was incorrect. The correct usage should have been the exact sequence. Okay, so let me correct myself. Okay, so let us first define exact sequences. This is something we had defined in the last class. However, I incorrectly called this as the Mayer-Vittoris sequence. Okay, so what is an exact sequence? An exact sequence is a sequence of vector spaces. Okay, let's say A0 to AM, and between these vector spaces we have these vector space homomorphisms eta 1 all the way up till eta m. Okay, and the eta I map goes from this vector space AI to AI minus 1. Right, so pictorially we can represent the situation as follows. So you have AM, which is a vector space, AM minus 1, which is a vector space, and you go all the way up till A0, and there are these vector space homomorphisms between AM to AN minus 1, AM minus 1 to AM minus 2, and so on all the way up to this vector space homomorphism eta 1, which goes from A1 to A0. Right, so this is the story, and we will say such a sequence is exact. Right, so when will we say such a sequence is exact? If such a condition holds. Right, so what is this condition? So let's sort of look at what is happening. So you have this vector space AI, right, and here you have this map eta I, and here you have this or let me look at so this is eta I. Yeah, so maybe I should look at AI minus 1. Okay, so that this is eta I minus 1 and this is eta I. Right, so so this sequence being exact means the following. Let's look at this scenario. You have this eta I minus 1 map. So eta I minus 1 vector space, and AI minus 1 vector space, and then there is this map eta I minus 1 which goes from AI minus 1, and then there is this map eta I which lands on AI minus 1. Right, so the sequence being exact means that for any such I, we require that kernel of eta I minus 1. Right, so kernel of eta I minus 1 is some subset of this AI minus 1, and then there is image of eta I. Right, so this is another subset of AI minus 1. These two things should be one and the same, and this should be true for every I. Right, so for every I, this relation should be true, and if this relationship holds, we will say that the above sequence is exact. Is that okay? So let me pause here for a second or two. If you have any questions with regards to this idea of exact sequences, please let me know. I'd be happy to answer. All right. Okay, so I don't see any raised hands, so let's advance. So what is a short exact sequence, right? So we define this notion of an exact sequence. Thereafter, we define this concept of a short exact sequence. So what is a short exact sequence? Well, it's a special case of an exact sequence. And in what sense is it special? It is special in the sense that in this sequence, right, we restrict ourselves to the case where m is 4, right? So if m is 4, I hope you agree that we will end up with 5 vector spaces, right? And more importantly, the boundary vector spaces, which is a0 and a4, we will assume them to be the trivial vector spaces. So again, I would like to emphasize that when I write this as 0, you shouldn't interpret it as saying that a4 is equal to 0. It's not equal to like saying some variable is 0, right? So notice that this is a vector space. A4 is a vector space. So when I write a4 as 0, this notation implies that a4 and a0, they are trivial vector spaces, which means that it's a vector space which only has one element, and we will think of that element as the additive identity. Okay, so that is very, very important. Please don't interpret this as saying like, this statement as equivalent to some other statement where we say, okay, some variable is 0. Okay, so that's not what the meaning is. I hope, based on the context, you can decipher what each statement means. Okay, so all these statements in different contexts mean different things. So you have to be very, very clear on what the context is, and accordingly figure out what this statement is. All right. Okay, so what is a short exact sequence? Well, it's a special case of an exact sequence. Special in the sense that we only have m equals 4, which means that we have 5 vector spaces, a0, a1, all the way up till a4. And furthermore, we have that these boundary vector spaces are the trivial vector spaces. Okay, so pictorially, the story is as follows. On the leftmost end, we have the trivial vector space, and on the rightmost end, we have the trivial vector space. And in between, we have these vector spaces a3, a2, and a1. And then there are these maps, which are your vector space homomorphisms, right? So, so this is short in the sense that the length of the sequence is small, right? And furthermore, this is also an exact sequence, which means that this relationship that we mentioned above, right, that holds in this case as well, right? So now we sort of said some or discuss some consequences of this sequence being short, right? So in particular, we said that because of the exactness property at a3, right? So what does that mean? So exactness property of a3 implies that kernel of eta 3, this should equal image of eta 4, right? So from this property, we discussed that, look, on the leftmost end, we have this trivial vector space. Eta 4 is a vector space homomorphism. So it should map 0 to the 0 of A3, right? And that should be the only element in the image of eta 4, right? So this means that, kernel of eta 3 equals image of eta 4. This must equal the set with only the trivial element or the additive identity. Sorry, I shouldn't say additive element, but rather the additive identity, right? So the kernel of eta 3 is trivial in the sense that it only includes the additive identity of this A3 vector space. All right. Now, because of this, we said that, okay, if the kernel is trivial, then it actually implies that this eta 3 map is injective, right? So injective actually means that this eta 3 map is 1 to 1, which means that if v and v prime are two elements in A3 such that v does not belong to v prime, then it necessarily implies that eta 3 of v does not equal eta 3 of v prime. Is this okay? So this is a consequence, and I proved this statement in the previous class, right? So similarly, we have some exactness notion at A1. So it is there at all the intermediate vector spaces. So we have now discussed the consequence of the exactness condition at A3. Now we are going to discuss the implication of the exactness condition at A1, right? So what is the exactness condition at A1 state? It states that kernel of eta 1, okay, this equals image of eta 2, right? So this is what it states. Now kernel of eta 1, right? So what does this map do, right? So on the right side, that is the rightmost end, you only have a vector space which only has this trivial element, that is this I mean the vector space which is trivial in the sense that it only has the additive identity, right? So and eta 1 has to map every element a1 to 0, right? That's the only choice that eta 1 has, and because of this reason the kernel of eta 1 is a1, right? So from this relation it follows that a1 is image of eta 2, right? So let's just try to understand what this means, right? What does this statement mean? Let's try to understand this, right? So we have a2 here, we have a1 here, right? And we have this a0 vector space, which is the trivial vector space, and eta 1 maps everything in a1 to 0, right? And we require that the kernel of eta 1, okay, should equal the image of eta 2, right? So what is the image of eta 2? So image of eta 2 is the set of elements in a1, okay, which get mapped to under this eta 2 map, right? And we require that the image of the image of eta 2 equal a1, right? So because of this condition, it must be the case that every element in a1, okay, lies in the image of eta 2, which means that there is at least one element in a2, okay, which gets mapped to this element in a1 under this eta 2 map, right? So every element should get mapped to some element in a2 under this eta 2 map, right? Of course it is possible that this could also happen, that there could be more than one element in a2 which gets mapped to the same element in a1, so that is not an issue. However, what we require is that every element in a1 has an element in a2 which gets mapped to it, okay? So that is what this requirement states. When I say this requirement, I mean this. So from this it follows that the exactness condition at a1 implies that eta 2 must be a surjective function. So surjective means that it should be a onto function, right? So onto function. So let me pause here for a second or two. If you have any questions with regards to this discussion, please ask. I would be happy to explain it again. So I hope it's clear that the exactness condition over here implies that eta 3 must be 1 to 1, and the exactness condition over here implies that eta 2 must be an onto function or a surjective function. Is this okay? So let me stop for a second or two. If you have any questions, please ask. All right, so let's advance. Okay, so let us draw the situation again so that we don't have to scroll up. So you have 0, a3, eta 3, a2, eta 2, a1, and eta 1, which is 0. All right. Okay, so this is the situation. Now, so far we have discussed or understood the implications of the exactness condition at A3, and we have also discussed and understood the implications of the exactness condition at A1. Right. So let's now try to discuss the exactness condition at A2 and what its implications are. Right. So the exactness condition at A2 implies that the kernel of eta 2, which is this map, it must equal the image of eta 3, right? This is a trivial consequence of the I mean, it's a consequence of the definition of the exactness condition at A2, right? So there is like nothing deep about this. This is just the definition of the exactness condition at A2. Now let's see, okay, what are the implications of these above conditions that we stated. Okay, so let's try to discuss this. Okay, so now what I'm going to do is I'm going to take A2, right, and I'm going to quotient it with image of eta 3, right? So let's first try to understand what is happening over here. So I hope you agree that image of eta 3, okay, this is basically the collection of elements in A2 which get mapped under eta 3, right? So the situation is as follows. You have A3 over here, you have A2 over here, and it is possible that these elements get mapped to a subset of A2, right? So the elements in A3 get mapped to a subset of A2, in which case this will be, right, the collection of these elements this will be the image of eta 3. Is this okay? Right? And notice that I have ensured that this map, that is this eta 3 map, okay, so this is 1 to 1. So I have ensured that every element in A3 gets mapped to a distinct element in A2, right? But we have not claimed that eta 3 has to be surjective, okay? So which means that it is possible that there is some element over here, okay, which does not get mapped to under this image, under this function eta 3, right? But every element, I mean eta 3 maps every distinct element in A3 to a distinct element in A2. That is something that must definitely occur. And furthermore, since eta 3 is a vector space homomorphism or a linear map, we have discussed this, that image of eta 3 is a subspace, okay, is a subspace of A2, right? So since it's a subspace and A2 is a vector space, we can indeed talk about this quotient operation, right? So that's the first thing. Whenever I talk about this quotient operation, you have to make sure that A2 is a vector space, and the thing with which I'm taking the quotient operation, this is a subspace of A2. Okay, so that much you have to verify, and that is indeed the case over here. Right? Now we know that because of this exactness condition at A2, image of eta 3 must equal kernel of eta 2, right? So if I took A2 and quotiented it with kernel of eta 2, whatever is the resulting vector space that I would have obtained, that would have been one and the same as this vector space that I would have obtained by taking A2 and quotienting it with image of eta 3. So why is that the case? Well, it is this statement is true trivially because image of eta 3 equals kernel of eta 2. So I hope you agree that these two statements are trivially true. Sorry, I shouldn't say these two statements. This statement is trivially true, right? Now the next thing I'm claiming is that if you take A2 and quotient it with kernel of eta 2, then this must be isomorphic to image of eta 2, right? So notice I'm not saying it is equal, I'm saying that it must be isomorphic, right? So isomorphic means that you take this vector space, you can construct a bijection from this vector space to this vector space, right? And that bijection will be a homomorphism, right? So we have an isomorphism between this vector space and this vector space. So now let's try to understand why or how we can claim that this vector space must be isomorphic to this. Okay, so all I'm going to say is that the dimension of this vector space must equal the dimension of this vector space, and then there is a result in linear algebra that if you have two vector spaces of the same dimension, then they must be isomorphic, right? So it is not very difficult to see how. You just identify a basis of the original vector space, you take a basis of the second vector space, and then you map each element in the basis of the first vector space to the corresponding element in the basis of the second vector space, and in that sense you would be able to construct this desired homomorphism. So now what I'm going to discuss is why is the dimension of this vector space equal to the dimension of this vector space. But this is something you already know, right? So why is the dimension of this vector space and the dimension of this vector space one and the same? Well, this is a consequence of what is called as the rank nullity theorem, right? So if you have heard about this rank nullity theorem, so it says that, let's say you have a vector space V, right? And let's say there is a map F, right, which goes from V to V prime. Then the rank nullity theorem says that dimension of V must equal the dimension of kernel of F plus the dimension of image of F. Is this okay? So in the context of matrices, okay, you must have studied it in the following way, that the number of columns must equal the column rank of the matrix plus the dimension of its null space, right? So this is the way you must have studied in the context of this matrices, this rank nullity theorem. But the rank nullity theorem actually holds true in the context of generic vector spaces as well. And it means the following. Let's say you have a vector space V and a vector space V prime, right? And let's say there is a linear map or a vector space homomorphism that goes from V to V prime. Then the rank nullity theorem says that the dimension of V must equal the dimension of kernel of F plus the dimension of image of F. Right? So this is the rank nullity theorem. So from this, I hope you agree that the dimension of this vector space and the dimension of this vector space are one and the same. Why is that? Because the dimension of this vector space, whenever we take this quotient operation, I hope you agree that the resulting dimension is dimension of A2 minus dimension of kernel of eta 2, right? And the dimension of this vector space is just dimension of image of eta 2. Right. So the rank nullity theorem says that these dimensions must satisfy this relation, and from this it is easy to see that dimension of A2 minus dimension of kernel of eta 2 must equal the dimension of image of eta 2. Right. So what I have shown is, here is a vector space, here is a vector space. These two vector spaces have the same dimension, right? And if they are vector spaces of the same dimension, just by that fact, one can show that these two vector spaces must be isomorphic. Right. So I'll pause here for a second or two. If you have any questions on how I argued this statement, please let me know. Yes, Jen, go ahead.
Oh, so why the image of neta 3 will be subspace of A2?
So your question is, why is the image of eta 3 a subspace of A2? Is that your question?
Yes, sir. Yeah.
So let's try to draw the diagram again. So we have this, we have 0, we have A3, we have A2, we have A1, and we have 0, right? And eta 3 is over here, eta 2 is over here, right? So your question is, what is image of eta 3, right? So image of eta 3, what is image of eta 3? Let me draw this pictorially. Okay, so you have this set A3, you have A2, right? So there are some elements in A3. So eta 3 will take every element in A3 and map it to A2, right? Some element in A2. That's what this job of eta 3 is. And we know that eta 3 is 1 to 1, but that doesn't matter for defining what image of eta 3 is. So you will have something like this, right? However, it is also possible that there is an element in A2 which doesn't get mapped to under this eta 3 image, right? So image of eta 3 is the collection of all these points. Is this clear, Jayant?
Yes, sir. Say, is that because of the property of eta 3 that makes it a subspace? Like,
so you are asking, so what was your question? Why is image of eta 3 a subset of A2, or is it a subspace? What is your question?
it's a subspace, right?
So it's a subset. That is trivial to see, I hope. It's a subspace because of the fact that eta 3 is a vector space homomorphism. It's a linear map.
Oh, okay. Yeah.
So we
Got
have
it.
proved this before, that whenever you have a homomorphism, right? I mean, yeah, I think I had given this as an exercise, that whenever you have two vector spaces, and I don't remember if the exercise was concerning vector spaces or it was concerning groups, but whatever be the discussion, the same discussion extends to vector spaces as well. So if A3 is a vector space, A2 is a vector space, and if you have a vector space homomorphism between them, then the image of this vector space homomorphism indeed will be a subspace of A2. Is that okay?
Yeah. Yes. Yeah. Thanks.
Okay, are there any more questions on how we arrived at this statement? Please let me know. This is a good time to ask. I'm happy to explain it again as well. So please don't hesitate. All right, so I don't see any raised hands, right? And now let's look at image of eta 2, right? So here is the story. You have A2, you have eta 2, right? And this is image of eta 2, right? So we know that eta 2 must be a surjective map, right? So image of eta 2 is a subset of A1, right? And we know that eta 2 is a surjective map, which means that image of eta 2 must be A1. Right. So from that fact, the fact that eta 2 is a surjective map, it follows that image of eta 2 must be equal to A1. Right. So from these above relations, I hope you agree that A2, when you quotient it with image of eta 3, it must be isomorphic to A1, right? I hope you agree that A2, when it is quotiented with image of eta 3, this must be isomorphic to A1, right? So since it is isomorphic, the dimension of this vector space and the dimension of this vector space must be the same. The dimension of the left vector space is dimension of A2 minus dimension of image of eta 3, right? This is the dimension of the vector space on the left, and the dimension of the vector space on the right is dimension of A1, right? And hence these two dimensions must be the same. That is dimension of A2 minus the dimension of image of eta 3. Okay, this must equal dimension of A1, right? However, eta 3 is an injective map, right? So eta 3 is an injective map. So let's try to understand what is injective. Okay, so this is the story. You have A3. Every element in A3 is mapped to a distinct element in A2, right? So there could be other elements in A2 which do not get mapped to under this eta 3 map, but nevertheless, whatever is there in A3, okay, that gets uniquely mapped to an element in A2. Right, so from this it follows that image of eta 3 and A3, right? Image of eta 3 and A3 must be isomorphic. Do you agree? Image of eta 3 and A3 must be isomorphic, hence their dimensions must be one and the same, right? Is this clear? So what we are saying is that since eta 3 is an injective map, right? So if you take A3, okay, and you look at the codomain to be the image of eta 3, right? So here this is a subset of A2. So earlier I wrote eta 3 to be a map from A3 to A2, but now notice that I have restricted my codomain to be just image of eta 3, and I'm looking at eta 3 as a map between A3 and image of eta 3, right? Now since I'm looking at eta 3 to be a map only onto this image of eta 3, I hope you agree that eta 3 will be both one-to-one and surjective, right? And it's already a homomorphism, hence it follows that eta 3, when it is looked at from this perspective, will be a vector space isomorphism, right? And because of this reason, A3 and image of eta 3 are isomorphic vector spaces, which means that these two vector spaces must have the same dimension, right? So from this, it follows that dimension of image of eta 3 is dimension of A3, and substituting this relationship over here tells us that dimension of A2 minus dimension of A3 equals dimension of A1, right? So in other words, whenever you have a short exact sequence, so let's try to understand this story. This is the summary, okay, but please don't by heart it. Please try to understand how we derived it. Okay, so this is A3, A2, A1, and then you have this zero map over here. Okay, so this relationship over here tells us that dimension of A2 equals dimension of A3 plus dimension of A1. Okay, so this is the conclusion of this discussion, or the implications of a short exact sequence. So whenever you have a short exact sequence, it automatically follows that the dimension of this intermediate vector space must equal the sum of dimensions of these vector spaces on either of its sides. Is that okay? So that's what this relationship is telling us. So let me pause here for a second or two. If you have any questions, please let me know. I'd be happy to answer them. Yes, Jacob, please go ahead.
Sorry, can you repeat that? Dimension of image of eta 3 is equal to dimension of A3. I didn't quite follow it.
So how about you try to argue it out loud, and I'll help you fill in the gaps, right? So what do we know about A3 and A2? Do you agree they are vector spaces?
Yes.
And what about eta 3? What do we know about it? It's a
okay, it's injective.
It's injective, and more than that, it's a vector space homomorphism. That's what we have been told. So it's an injective map, which means it's a one-to-one map, and it is a vector space homomorphism. So these two properties we have already been told. Is this okay? Right?
Okay.
So now what we have is, this is A3, this is A2, right? So this entire thing gets mapped to this a smaller region, right? So it is possible that image of A2 is only a subset of, image of eta 3 is only a subset of A2. Do you understand this picture?
Yes.
Right. So now what I'm saying is that this map over here, which is eta 3, is 1 to 1.
Yes.
And it is also surjective. Surjective when you look at the codomain as image of eta 3.
Okay, only that particular portion. Okay.
Yeah, so if you only look at that particular portion, which means that if you think of eta 3 as a map that goes from A3 to image of eta 3, I'm saying this map is surjective.
Yes.
This
so
is trivially surjective, right? I mean,
okay,
right?
so the dimension must be same since it's bijective and homomorphic.
Since it's bijective and it's a vector space homomorphism, it follows that eta 3, this map, okay, so this map, which means that when you think of eta 3 as going from A3 to image of eta 3, right? I'm being very, very careful over here. Eta 3, when it goes from A3 to A2, we cannot think of eta 3 as a isomorphism. Do you agree?
Yes.
However, this map can be thought of as an isomorphism. And since isomorphism, intuitively means that the domain and the codomain vector spaces are one and the same in one sense, right?
Yes.
So their dimensions must be one and the same. That's all I have written over here.
Yes.
Is this okay?
And also, why is this result important?
So we will see this importance of this result in stating this Mayer-Vittoris theorem. Is
Okay.
this okay? So so our goal at the end of the day is, slowly building up towards this Mayer-Vittoris theorem. I mean, I cannot state it directly because the theorem says, something is an exact sequence. Because of that, these dimensions relationship is true. Is this okay? So we won't be able to directly understand what those things are, why it is true. So what I'm saying is that first I gave you the purpose of this Mayer-Vittoris theorem, and now I am giving you some background knowledge so that you are able to appreciate and understand what the statement of the Mayer-Vittoris theorem is. At this point, you should know what do I mean by an exact sequence. You should understand what do I mean by a short exact sequence, and you should understand the implications of a short exact sequence. And the summary of the implications is the following, that the dimension of the intermediate vector space is the sum of dimensions of the vector spaces on either sides of this A2. That's all you have to understand at this point. Is this okay?
Okay.
Okay. So yes, Jen, please go ahead.
So here we can't say the dimension of image of eta 3 is equal to the dimension of A2, right?
We cannot say that. So if your question is dimension of image of eta 3 equals dimension of A2, so this we cannot say, because it is possible that the dimensions are the same, but it is also possible that the dimensions are different. We cannot say that. Neither of them is true, because unless we have additional information, we cannot say this. Is this okay? But we can definitely say that this is true. Okay, I hope you agree. This is always true. That dimension, let me correct it and write it properly. That dimension of image of eta 3 must be less than dimension of A2. That is definitely true. I hope you agree.
Yes, sir.
Right, this follows because image of eta 3 is a subset of A2, right? So if you have a subspace sitting inside another, if you have a vector space sitting inside another vector space, okay, the inner vector space cannot have a bigger dimension than the outer vector space. Okay, so from that fact, it follows that this dimension relation must be true. All right, so let me stop here for a second or two more. If you have questions, please ask. So at this point, it's not clear why this short exact sequences are useful and all. So I can only say that, at the end of the day, when I state this Mayer-Vittoris theorem, I will be speaking in the language of short exact sequence, and, somehow saying that, look, this is a short exact sequence means that, such a relationship must be true. And from that, the dimensions of, some vector spaces will be the same, and you will be able to visualize, okay, the dimension of these vector spaces are the Betti numbers of our interest. So recall what I said, the Mayer-Vittoris theorem somehow says that if you can somehow decompose this, X as, let's say A union B, where both A and B are subcomplexes, and we would like to know in some sense, what are the Betti numbers of X, okay, if you somehow know the Betti numbers of A and B, right? So at the end of the day, Betti numbers, recall, are dimensions of these homology spaces, right? So they are the dimensions of the homology spaces, and such relationships will be useful to understand the relationship between the Betti numbers of this simplicial complex in terms of the Betti numbers of this simplicial complex. Okay, so I'm not giving you the full story because it's not possible to give the full story. The reason being there are too many technical terms that still need to be defined. All right. So now we can advance. Okay. So now, I'm going to state a fact. Okay. I won't have, time to prove it, but let me just state a fact, and it should be possible for you, to prove this on your own. I don't expect you to be able to prove it, but those who are interested, okay, can go back home and, see if they can prove it on their own. So what is the statement? In the way we discussed what happened above, okay, one can similarly show that, let's say if you have an exact sequence of the following kind, right? So you have A4, A3, A2, A1, A0. So there are 5 vector spaces, and then there is a sequence of maps which go from A4 to A3, A3 to A2, A2 to A1, A1 to A0, right? So this is not a short exact sequence because I'm not assuming that these boundary vector spaces are trivial. I'm not making that assumption. Okay, so this is some exact sequence, right? Just the fact that it has 5 vector spaces, that is true. However, I'm not making this assumption that these boundary vector spaces are trivial. Because of that reason, you will not think of this as a short exact sequence. One more thing, each of this indeed is a vector space, but you must have noticed that I have not written any notations for the maps between A3 to A2 and A2 to A1. Okay, so this does not mean that there are no maps here. Indeed there are maps, only then I hope you agree that one can call this as an exact sequence, right? So one should have this eta 3 over here and eta 2 over here. So there are such maps. However, I don't want to write it because on one hand, okay, I don't want to unnecessarily introduce too many notations, and on the other hand, the result that I will now state, okay, only can be expressed only in terms of this. However, when you try to prove this, you will have to make use of all these intermediate vector spaces. Okay, so I hope that is clear. So I'm not explicitly highlighting what these maps are. However, there are all these maps also exist and they will be needed in the proof. However, these maps are not needed to state this result, which I'm going to do now. All right. Okay, so let's say we have an exact sequence of the following kind. So we have 5 vector spaces and some linear maps between these vector spaces, and this is exact, which means that the kernel of this map over here equals the image of this map and so on, right? So suppose we have such an exact sequence, then the statement is that this sequence is a short exact sequence. Okay, so that's the claim. If you have this sequence as an exact sequence, then this sequence is a short exact sequence. Now let's try to understand the different entities in this short exact sequence. So whenever I say something is a short exact sequence, it automatically follows that we will have 5 vector spaces and the boundary vector spaces are going to be the trivial vector spaces. Okay, so that follows by default. So that's why I've written 0 over here and 0 over here. So these are your trivial vector spaces. So far so good. Now there is something called A2 here. Well, this A2 is precisely this A2, right? So we have managed to understood this vector space, and this vector space, right? Now what is kernel of eta 1? Well, you have A1 over here. Eta 1 is a map that goes from A1 to A0, and eta 1 is a vector space homomorphism. So one can talk about its kernel, right? So kernel of eta 1 is also a vector space because it's a subspace of A1. So here you have kernel of eta 1. So you have A2, you have kernel of eta 1 over here, right? So these 4 vector spaces are now clear. Now the only thing that remains is what is this vector space over here. The way to first pronounce this is the following. You have to call this as the co-kernel of this vector space homomorphism eta 4, right? So when I write COK eta 4, you have to read it as co-kernel of eta 4. And how is it defined, right? It is defined in the following way, right? So you take A3 and you quotient it with image of eta 4, right? So let's just see what is happening. So A3 is over here image of eta 4 is a subspace of A3. So indeed this quotient operation is well defined, and you can now this quotient operation is well defined, and this is the definition of the co-kernel of eta 4, right? So the first thing you have to observe is, why don't I call it as the kernel of eta 4 or something like that? Well, I don't call it as the kernel of eta 4. The reason being, kernel of eta 4, I hope you agree, is a subset of A4, right? Kernel of eta 4 is a subspace of A4, right? So that's why this thing I cannot call it like the kernel of eta 4, right? So this thing, okay, A3 and image of eta 4, okay, these are I mean A3 is a vector space and image of eta 4 is a subspace of A3. So one can now take the quotient operation. So this is well defined, and in some sense this is related to eta 4, right? This is related to eta 4 because you are taking the quotient with respect to the image of eta 4, right? And so I mean that's the reason. But I won't have time to spend and explain why this is called co-kernel, what does this co-kernel mean and all. Okay, so that is part of some algebra course. But in case you are interested, you can look it up on Wikipedia. But at this point, you can just think of this as being some definition. Okay, in the study of homology, why this is called co-kernel and all, is not really that important. Okay, so what is important at this point is the definition that this co-kernel of eta 4 is the quotient of A3 with respect to image of eta 4. Okay, so now let's read the statement again. The statement says that if this is an exact sequence, then this is a short exact sequence where the co-kernel of eta 4 equals the quotient of A3 with respect to this image of eta 4. Okay, so that's what this result is. Right now, using this result, okay, you can also use this result and use this result and say something about the relations between the dimensions of different entities that are involved over here. Okay, so we will sort of derive this later and sort of understand what are the implications of the dimensions of these vector space, this vector space, and this vector space, and so on. We will sort of derive it later, very close to when we state this Mayer-Vittoris theorem. Okay, so at this point you just have to understand that if this is a exact sequence, this is a short exact sequence. Okay, so let me pause here for a second or two. If you have any questions in understanding what this statement is trying to tell you, I'd be happy to explain. Yes, Pankaj, please go ahead.
Since you have already said the A4 vector space and A0 vector space is already trivial vector space, so
sir, they are not trivial. These are some generic vector spaces.
No, the other one.
Yeah, in this the boundary vector spaces are trivial. Yes.
Yeah. So what needs to be shown here to prove this as a short exact sequence? Because I thought like if those two are trivial vector space, then this is already a short exact sequence.
Okay, so your question is, if the boundaries vector spaces are trivial, doesn't it automatically follow that this is a short exact sequence? Is that your question?
Yes.
So that is not true. Okay. Yeah. See, we have to first show that this is an exact sequence. Okay, so what does that mean? Exact sequence means you have to first figure out what the vector space homomorphism over here is, what the vector space homomorphism over here is, right? And then you have to check if at each of these intermediate vector spaces, does the kernel of this vector space homomorphism equal the image of this vector space homomorphism? Is this okay? So that you have to verify for each of these things and make sure that it's an exact sequence. Does that answer your question, Pankaj?
Yes, thank you.
Right, so that needs to be verified, and this theorem says that this will actually be true. So I'm not giving the proof of this. All I'm saying is that if you if you sort of define these intermediate vector spaces, okay, intermediate vector space homomorphisms, and if someone tells you that this is an exact sequence by some series of algebraic operations, you will be able to show that there will be some induced. So first of all, I have not even told you what these vector space homomorphisms are. right? So all this will require some substantial discussion, and in this course we don't have the bandwidth for this discussion. Is this okay? Because this is part of algebra, so I don't want to spend too much time, what would be the induced maps and so on. Okay, however, to answer your question, there are some induced maps which will be induced from this eta 3, eta 4, eta 3, eta 2, eta 1. So this will induce some maps over here, which will be vector space homomorphism. So we will have to show that those continue to be vector space homomorphism. And for these new vector space homomorphisms that are induced over here, this sequence is exact in the sense that, at each of these vector spaces, the kernel of this map and the image of this map, they are equal. The kernel of this map and the image of this map are equal, and so on. Okay, all right. Deep, please go ahead.
Yeah, I was just wondering, so in general, if I have an exact sequence, this is a recipe to extract the short exact sequences, right? Because A0 and A4 need not always be trivial. So this is the way I could extract these short exact sequences.
Yes, right, that's true.
Okay, and I think last time also it was asked, I couldn't understand. So why exactly are we looking at m equals to 4? I didn't understand that.
So your question was, why is this short exact sequence special? Is that your question?
No. I mean, if we say short for m equals to 4, right? So why is that? I didn't get that. I mean, I looked up on Wikipedia also, but there's not really any explanation. So just wondering.
This short and long are just some terms that people use. Okay, this is just for convenience. There is as far as I understand, there is no really deep meaning to why it is called as short. Okay, so intuitively it's called short because this is a sequence which is not very long. Okay, so in the sense that it has only 5 vector spaces. More importantly, the boundary vector spaces are trivial. But why is this? Why is it called a short exact sequence? I'm not really sure if I also have a good answer. But I can tell you that this is an important thing because you will see that when we state the Mayer-Vittoris theorem, you will be able to see how we make use of this fact. Right there, in fact, we will see we will end up having such a short exact sequence. We will actually use this theorem over or this claim over there. So we will have something like this. From there, we will say that if this is an exact sequence, this must be a short exact sequence. And if this is a short exact sequence, the dimension of this intermediate vector space must equal the sum of dimensions of these vector spaces. So that property we will use. Right. So why is this important? Well, this is important because this is sort of this plays a very key role in the Mayer-Vittoris theorem. Is that okay? It's not very important outside, if I'm correct, outside this Mayer-Vittoris theorem. Is that okay?
Okay.
All right. Okay, so far so good. These are things that you are studying for the first time. It's fine, but you can ask, why are we studying this in the computational homology class? That's a very, very valid question. You will see that at the end of the day, we discuss this Mayer-Vittoris theorem, and based on the Mayer-Vittoris theorem, we will come up with an algorithm for computing these Betti numbers in an incremental fashion. Okay, so this is this algorithm, and this algorithm, I hope you agree, is indeed of interest to a student in computational homology course. Right, so these algorithms will help you actually compute these Betti numbers in an incremental fashion. What incremental means and so on and so forth, I will be a bit more clear about this when we discuss this algorithm. But I would like to state that this is a very, very popular algorithm, and this was stated in the year, if I'm not wrong, 1992 or 93 by Adelsbrunner and Delfinado. Right, all right. So far, so good. Okay, so now the next concept that we need is that of a chain complex, right? So again, you can ask, why are we talking of this chain complex and things like that? So again, the answer is the same. We require all this to state this Mayer-Vittoris theorem, right? So that's why we need to understand what this chain complex and things like that are. Right, so what is a chain complex? Well, this is something you already know, but maybe I didn't call it as a chain complex. Right, so recall that. Let's go back to our original setup. We have these, this abstract simplicial complex, and we can construct this chain spaces. Right, so for any p in the set of integers, we can define a vector space which we refer to as the chain space CP. This is the set of all possible p chains. Right, p chains. Right, so this is a vector space, and then we have a vector space homomorphism, which is this boundary operator which goes from the p chain space to the p-1 chain space. right? So so far we looked at these boundary operators as individual entities, but I hope you agree that we can look at them in the form of a sequence, right? So what happens over here, you start from CP, I mean let's say this sequence is of infinite length, so it goes in either directions, okay, forever, right? So the part of the sequence looks like this. Let's say you are at CP, right? So daba p plus 1 will come from CP plus 1 and map to CP, right? So then you have daba p which goes from CP to CP minus 1, and you have this daba p minus 1 which goes from CP minus 1 to CP minus 2, and so on. And somewhere in between we will also have C2 to C1, C1 to C0, and so on, right? So this entire thing together is referred to as the chain complex. Is this okay? So when we only look at these things as individual vector spaces and vector space homomorphisms, that's what we have done so far. However, you can also look at them as one whole thing, right? And this whole thing we will refer to it as the chain complex, right? So why do we need chain complexes? Well, we can now talk of functions between chain complexes, right? So let us talk about what are called as chain maps, right? So what is a chain map? Okay, so what is a chain map? For that we need two chain complexes, right? So let's denote this chain complex as X and Y. So whenever I say X is a chain complex, what does it mean? X itself has a sequence of vector spaces xn, xn minus 1, xn minus 2, and so on. So it continues in either direction to infinity. And between these vector spaces you have some vector space homomorphism. Furthermore, okay, you have the property that f when it is applied twice is identically equal to 0. Okay, so this property is necessary for when we have a chain complex. So X is a chain complex. So notice I have written X over here. This refers to this entire chain of vector spaces and the vector space homomorphisms between them. Similarly, Y represents another sequence of vector spaces and the vector space homomorphisms between them. Is this okay? So X and Y are two chain complexes, and now we have a function from this chain of vector spaces and this to this chain of vector spaces. So we will refer to this as this phi function which goes from X to Y, right? So this is written in this fashion. However, X here is this chain complex and Y over here is this chain complex. So when would I say we have a chain map from X to Y? Well, this itself is a sequence of homomorphism. Whenever I say phi is a chain map, it itself is a sequence of homomorphisms. In what way? Well, phi is made up of a sequence of maps phi n which goes from xn to yn, and the following diagram commutes. Okay, so let's, this is too much information in one go, so let's break it piece by piece. Okay, so on the top you have the X chain complex, right? So you can see that you have these vector spaces xn plus 1, xn, xn minus 1, and so on, and you have these vector space homomorphisms between them. So far so good, no issue. And you have this chain complex as well. So at the bottom you have yn, yn plus 1, yn minus 1, and you have these vector space homomorphisms between them. So this is a chain complex, this is a chain complex. And now we are trying to define a function between this chain complex and this chain complex. Okay, so what is this function? Well, it is referred to as if we refer to it as this phi function. However, the phi function is made up of a chain of functions. Okay, and this phi n function goes from xn to yn. So xn is a vector space, yn is a vector space, and phi n over here is a vector space homomorphism. We don't stop over there, right? So we also require that not just that these functions be vector space homomorphisms, we also require that this diagram commutes, right? So this diagram actually commutes. So what does it mean to say that this diagram commutes? So whenever I say some diagram commutes, you have to sort of picture in your mind that if you traverse this diagram in more than one way, the result would be the same. That's what this commute property means. Okay, so in this specific case, what does it mean? So let's say you start at xn, okay, and proceed in this direction, right? Alternatively, let's say you start in let's say this direction. Okay, so in you start at xn, so notice that the source and the destination are the same. The source is xn and the destination is yn minus 1. So when I say this diagram commutes, it means that if you start from xn and traverse this green line, okay, whatever is the output that you end up with, okay, that would be the same output that you would have obtained if you traverse this light blue highlighter line. Is this okay? So that's the story. Okay, so formally, what does it mean? It means the following, right? So you take Gn, compose it with this phi n operation. So I hope you agree that Gn composed with phi n takes an element xn and maps it to yn minus 1. Similarly, you take the composition of phi n minus 1 with fn, right? So you take fn, take an element in this, map it to this, and then apply this phi n minus 1 operator, and you go to yn minus 1. So this commutative property means that these two functions are one and the same. So two functions are one and the same means that if you give an input to this, whatever is the output, that would be the same output if you gave that input to this function as well, right? So in other words, Gn of phi n of let's say x, right? This must equal phi n minus 1 of fn of x for every x in xn, right? This is what this property means. So let me pause here for a second or two. Let me know if you have any questions with regards to this chain map. Yes, Jacob, please go ahead.
Can we go from xn plus 1 to yn minus 1 and still get the same results?
Xn minus 1 to
xn,
yn, I mean
xn plus 1 to yn minus 1.
So you are saying, let's say we go like this, right? Yeah. And we go like this. Would we end up with the same answer?
Yeah.
So what I will do is I will encourage you to think about it. Okay, that does the commutative. So at this point, the commutative property only implies that implies something with regards to this. Is this okay? It only implies something with regards to these two directions. Now your question is, if I traverse in this direction or if I traverse in this direction, would I end up with the same answer? So what I will do is I'll allow you to think about it and see if this condition implies your statement. Is that okay?
Okay.
Right. So you just have to verify something very trivially. Let's say there is an element, x over here. So what you do is you take fn plus 1 of x, right? Right, and then what you, so fn plus 1 of x will be an element in xn. Then you apply fn, right? So this will be fn of fn plus 1 of x. Then you apply phi n minus 1. So phi n minus 1 of fn plus 1 of x, right? So this is one way of traversing this diagram. Do you agree, Jacob?
Yes.
Right, so this is the way of, now what you're asking is, let's say I traverse this diagram in the following way. So let's say I traverse it in this way, right? So what I will end up with is, I will end up with phi n plus 1 of x, right? And then I will apply this gn plus 1 map, right? And then I will apply this gn map, right? And the question is, are these two things one and the same or not, right? So I encourage you to verify it on your own. The definition only concerns this kind of traversals. Is that okay?
Okay.
So you should be able to verify whether it is true or not. Okay. All right. Yes, Pankaj, please go ahead.
Yeah, the property that you said f2 is equal to 0.
Yes.
Like that is for the same function or two subsequent functions?
So f2 equals 0. Okay, so as I said, mathematicians are quite lazy. They want to write things in the laziest possible fashion. However, you should be able to decipher it unambiguously. So let's try to understand. So what does this mean, right? So first of all, there is no f, right? So the first thing is, you have only these fn. So fn goes from xn to xn minus 1. Right, so what does this f2 identically equal to 0 mean? It doesn't mean that you apply fn twice. Can you apply fn twice, Pankaj? What do you think? Can we apply fn twice? No, because the output of fn is in xn minus 1. So you cannot apply fn to xn, an element in xn minus 1. Do you agree? So f2 means that you are taking fn minus 1, compose it with fn, and this should be 0. and this should be true for all n. That's what this condition means. Is this okay? Does that answer your question, Pankaj?
Yeah. I think I'm missing something, but if I apply this function twice, then from the second step onwards, everything will be 0, right?
That is true. So you are you talking about this thing?
Yeah, yeah.
Yeah, so that is true. So that's what I asked you to verify on your own. I didn't say whether it is true or not. So you are right that this would be 0. If that was your question, this would be 0. Yes, that is true. Okay. But nevertheless, you can verify whether this holds or not. Do you agree?
Yeah.
Right. So I mean, I think Pankaj sort of already answered this. So fn of fn plus 1 is 0. So what? And now you are saying phi n minus 1 of 0. So what should be this? Pankaj, what your answer should be? This should be
0.
0. And what should this be? We don't even have to care about what phi n plus 1 of x is because we are applying gn twice. So this also should be 0. Do you agree?
Yeah.
Yeah. So then it is trivially true that something like this must hold. Okay, but but I think Jacob asked a more important question that what will happen if I traverse in this direction, right? Is that right, Jacob?
Yes.
So you can traverse in either of several of these directions, but then this part if you traverse in this direction, this must equal this. That is trivially true from this property. Is that okay?
Okay.
Right. Okay, but I would like to also emphasize that notice these directions are very, very important. Notice that at no place have I put this, directions on either side of the arrow. So that is also very, very important. So you cannot like traverse in this direction. Okay, so this is not possible because this arrow doesn't tell you how to move upwards. Is that okay? So please don't, ask why will this, what will happen to this? Well, this is not defined. You cannot move in this direction because that direction of the arrow tells us that this map over here takes an element xn to yn. It's not the other way around. So it is possible that this phi n maps, they are not invertible. If they are not invertible, you do not know how to move upwards. Is this okay? So let me pause here for a second or two. If you have any questions on a chain map, please let me know. All right. So now what we will do is, so keep this diagram in your mind. I mean, if you have some writing pad or something like that, you may want to note this down. Okay. So now we are going to study some implications of having such a chain map, right? So what are the implications of the chain map? Okay. So I'm going to help you prove some claims, but most of these claims are very trivial. So I will prove one such claim. There is also another claim which, while I have given its proof, I will leave it as an exercise for you to go back home and read it on your own. Okay, so let's look at this claim. So this claim says that if x lies in the kernel of fn, right? So let's try to understand what is happening. So you have fn, you have the kernel of fn. So recall what is kernel of fn. So kernel of fn is all those elements in xn such that fn of x is 0, right? So this is how the kernel of fn function is defined, right? So this is how kernel of fn is defined. And we are saying that let x lie in the kernel of fn. So this means that x is an element of xn such that it is mapped to 0 under the fn map. Is that okay? It is mapped to 0 under the fn map, right? So what this theorem tells us is that you look at x, you take its image under the phi n operator. So this is phi n of x. So this phi n of x will actually lie in the kernel of gn, right? So let's just try and understand. So there is something happening on the top, there is something happening on the bottom, and we are trying to relate what happens on the top with what is happening at the bottom. So what this result is saying is that, let's say you have some x which lies in the kernel of fn. You map this x, right? So you map this x to phi n of x. So I hope you agree that phi n of x is an element of yn. And the claim is that phi n of x will lie in the kernel of Gn, right? That's what this theorem tries to tell us. So let's try to prove this. So it's very, very easy. So since x lies in kernel of Fn, right, it automatically follows that Fn of x is 0, right? So here you have x, right? So let me draw this part of the diagram. So this is xn, this is xn minus 1, this is Fn, and this is yn minus 1, this is yn, and this is phi n, and this is Gn. Right? So what we know is that Fn of x must be 0. So you started off with some x, this got mapped to 0. Okay, so that's all we know. Now we know that so this phi n minus 1 is a homomorphism. It's a vector space homomorphism, which means that you take this 0 and map it to the 0 over here. Right? So let me draw this. So this is the additive identity of this yn minus 1 space, and under phi n minus 1, this 0 has to get mapped to this 0. Okay, so that's the default property of a vector space homomorphism. Right? Now we know that this diagram commutes. Right? So if this diagram commutes, it follows that if x gets mapped to phi n of x over here, okay, and if you apply this Gn on this, so you would end up with Gn of phi n of x. Now this must equal whatever is the result over here. Right? So what we end up with, because this diagram commutes, we can conclude that if you take Gn composed with phi n and you apply it on x, this must be 0. Right? So all we are saying is that if you traverse in this direction, or if you traverse in this direction, you end up with the same result. So I hope you agree that Gn composed with phi n of x. So this is equivalent to, you first apply phi n on x, whatever is the result, you apply Gn. So this must equal 0. Now if this must equal 0, this automatically implies that phi n of x must lie in the kernel of Gn, because that's the definition of kernel of Gn. Right? So and this proves the claim. Right? So this claim is true. So let me pause here for a second or two. If you have any questions with regards to this claim, please let me know. So if you have any questions with regards to the statement of the claim or to the proof of this claim, please let me know. As you can see, everything is very straightforward. The proofs are very, very easy. Right? So the only thing that is difficult is you have to understand what these definitions mean. Right? So once you understand these definitions, the proofs are very, very straightforward. I'm not, I mean, there is nothing deep in this proof. It's just, making sure you understand this commutative property correctly and invoke it in the right sense. So do you have any questions? All right, so I don't see any raised hands, so maybe we can advance. Okay, so we have a similar claim in the following sense. So I will just draw the diagram, and I will not prove it. I'll sort of allow you all to prove it. So let's say you have xn plus 1, you have xn over here, and here you have fn plus 1, and here you have phi n, here you have phi n plus 1, here you have yn plus 1, and here you have yn, and this is Gn plus 1. Right? So what this result says is that, let's say x lies in the image of Fn. Right? So here you have x, right? And we are saying that x lies in the image of Fn. Right? So which means that maybe there is some x prime here which gets mapped to x, right, under this map Fn plus 1. That's what it means to say that x lies in the image of Fn plus 1. Right? So what this result says is that if x lies in the image of Fn plus 1, then wherever x gets mapped to, okay, so let's say this is phi n of x. So then phi n of x will also lie in the image of Gn plus 1. Right? So you can see that when because this diagram commutes, whatever happens at the top, okay, has some corresponding story in the chain complex that is there at the bottom. Right? So if x lies in the image of Fn plus 1, phi n of x lies in the image of Gn plus 1. Okay, so the proof is again very, very short, as you can see. Okay, so you can read it on your own. If you have any questions, you can ask me. However, I'll pause here for a second or two. If you have any questions with regards to the statement of this claim, please let me know. Okay, the proof I have written it down. I encourage you to go back home, read a bit about it, and if you have any questions, you can ask me. Okay, so I'm stopping here, and you can ask me questions on the claim. All right, so I don't see any raised hand, so maybe we can advance. Right, so now let's try to summarize the the properties of this chain maps. Right, so let's just understand what is happening. Okay, so now there is something on the top, right? So you have xn plus 1, you have xn, you have xn minus 1, and so on, right? So you have xn minus 1 and so on. Right, now we know that this f and g maps, right, they satisfy the condition that if you apply f twice, this is the identically zero operator, and similarly if you apply g2 twice, it's the identically zero operator. So this statement, for example, automatically implies that the image of fn plus 1 must be a subset of kernel of fn. So let's draw this pictorially. So pictorially, what is happening? You have xn. This is a vector space. Okay, so I'm representing it as an oval shaped thing. So there are elements within it, right? Now, kernel of fn and image of fn plus 1, these are subspaces, right? So I'm representing it by the red and green oval shaped things, right? And we also know that image of fn plus 1 is a subset of kernel of fn. So you can see that I have put this image of fn plus 1 as a subset of kernel of fn, and that itself is a subset of xn, right? So these are not just subsets. One can verify that these are also subspaces. So image of fn plus 1 is a subspace of kernel of fn, and kernel of fn is a subspace of xn, right? So this property holds. So this property, or this picture, okay, is just a consequence of the fact that f2 is identically 0, right? Now a similar picture can be drawn in the context of the function g. Now because g is 0, one can sort of have this outer shell which represents yn, right? So you can have this inner circle which represents this kernel of gn, right? And then you have this inner shell which represents this image of gn plus 1, right? So you have this picture at the bottom, right? So when I say at the bottom, in a chain map, you have a chain complex at the top and the chain complex at the bottom. So this is the story with regards to the chain complex at the top, and this is the story with regards to the chain complex at the bottom, right? However, there is also some connection between what happens at the top and what happens at the bottom, and that connection is via the two claims that I stated. Okay, so let's try to summarize what the two claims are. So the claims were, if x belongs to kernel of fn, then phi n of x belongs to kernel of gn, right? So let's try to interpret what this means, right? So it means that if you look at phi n of kernel of fn, right? So let's try to understand what this object over here is. So I hope you agree that kernel of fn, this is a set, right? So it's a collection of all those elements in xn such that fn of x is 0, right? Now what is phi n of kernel of fn, right? It's the collection of phi n of x such that x lies in kernel of fn, right? So this also is a set. So this is how I define phi n of kernel of fn. So phi n of kernel of fn is the collection of phi n of x, that is phi n applied to x where x lies in kernel of fn. This is how I define phi n of kernel of fn. Now this property tells us that if x is an element of kernel of fn, the phi n of x must be kernel of gn. So which means that every element in this set must lie in kernel of gn, right? This is what it means. So accordingly, we can say that phi n of kernel of fn is a subset of kernel of gn, right? So this is what is true. So accordingly, what we can do is, we can draw this dotted circle over here, right? So we can draw this dotted circle which represents the phi n of kernel of Fn, and this would be a subset of kernel of Gn, right? And similarly, there was another claim that we had made above. So the claim above was the following: if X lies in image of Fn plus 1, this implies phi n of X lies in image of Gn plus 1, right? So in the same way, this statement can be written as follows, that phi n of image of Fn plus 1, this is a set, okay, this is a subset, okay, of this is a subset of image of Gn plus 1, right? So one can sort of easily see that this is a subset of this. This is in the same way I describe this relationship, right? So this is in the same way. So what I do over here is, you look at this green shell. This represents the image of Gn plus 1. I have drawn this dotted shell within it, which represents the phi n, which represents phi n of image of Fn plus 1. Right. So in this way, you can sort of interpret the story that connects what happens on the top to what happens at the bottom. You have these 5 shells. You have Yn, you have kernel of Gn, you have phi n of kernel of Fn, which is the shell within this red shell, and then you have image of Gn, and you have phi n of image of Fn plus 1, which lies over here. Right. So now one can ask, we understand that this dotted oval shaped thing lies within the solid oval shaped thing, that is clear. But is it true that the solid green region will always lie in this dotted red region? Well, the answer is that that is not always true. It is also possible that this dotted red region lies within this solid green region, right? So I've just stated this as a comment over here. Okay, so let me so if you have any questions with regards to these pictures, let me know. I mean, this is just a pictorial representation of the 2 claims that we made above. Okay, so if you have any questions, please let me know on what do I mean by this, and so on and so forth. Please let me know. All right. Okay. So I don't see any raised hand. So in the remaining 10 minutes or so, we will discuss the last topic for the day. Okay, which is concerning this induced homomorphism. Right. So notice that this Mayer-Vittoris theorem, okay, whenever we will state, okay, it will somehow relate the Betti numbers of different simplicial complexes, right? And Betti numbers, recall, are the dimensions of these, these homology spaces, right? So now we have these chain maps, right? So these chain maps have these, oh, it is too far back. Okay, so these chain maps have something at the top, something at the bottom. So I hope you agree that with regards to the chain complex on the top, you can define this homology spaces. So you can define Hn of X. This will be defined as kernel of Fn quotiented with image of Fn plus 1. Okay, so this is how we defined the nth homology space. It was the quotient of this kernel with regards to the image of quotiented with regards to with respect to the appropriate image. So this is how we will define this Hn of X, and similarly we can define Hn of Y, right? So this is kernel of Gn, and you quotient it with image of Gn plus 1, right? So this is how we can define the homology spaces with regards to the chain complex on the top, and the homology spaces with regards to the chain complex at the bottom. And now the question is, how are the homology spaces defined at the top and the homology spaces defined at the bottom related? Okay, so that is the question, and that is what I'm going to answer now. Okay, so in order to do that, the first thing we will understand is something called as the induced homomorphism. Okay, so let me try and explain what do I mean by that. Okay, so you have this this chain complex xn plus 1, xn, xn minus 1, and so on, and you have this chain complex yn plus 1, yn, yn minus 1, and so on, right? Now, with regards to this, the top chain complex, I hope you agree that you can come up with this Hn of x, Hn of Hn minus 1 of x, and so on, right? So you can come up with these, these vector spaces which correspond to the homology spaces associated with the top chain complex, right? And similarly we can come up with these these homology groups associated with the chain complex at the bottom, right? So you have Hn of y, you have Hn minus y of Hn minus 1 of y, and so on, right? So one can ask, well, there are these maps between these spaces. Can we say something about the map between Hn of x and Hn of y? So is there any relation between Hn of x and Hn of y? Similarly, is there any relation between Hn minus 1 of x and Hn minus 1 of y? Okay, so that is the kind of question that we are now going to answer. Is this okay? So in order to understand that, let's try to see what are the elements in Hn of x, right? And how can we relate it to the elements in Hn of y? Right, and recall that Hn of x is basically the kernel of Fn, and quotient it with image of Fn plus 1, right? And similarly, Hn of y is equal to kernel of Gn quotiented with image of Gn plus 1, right? So I'm saying this because in the above picture we somehow saw the relation between kernel of Fn, kernel of Gn, image of Fn, and image of Gn plus 1, and you can see that we are somehow taking these related or the entities that we spoke about, and we are using this to form this quotient space and end up with this Hn of x and Hn of y. Right, this is how we end up with. So let's try to understand how are the elements in Hn of x related to the elements in Hn of y, right? So in order to do that, let's first take an element of Hn of x, right? So I hope you agree that Hn of x is obtained via this quotient operation, which means that the elements of Hn of x will be equivalence classes. So let us take one such equivalence class, right? So and let's denote this as square bracket x. So this is an equivalence class in Hn of x. So what does this mean? This means that this is a set. And what is this set? Well, first let's define what this x is. Well, this x must lie in kernel of Fn. Furthermore, this x over here is the collection of all those elements x prime in kernel of Fn, such that the difference, that is x prime minus x, lies in image of Fn plus 1. So I'm just using the definition of this quotient operation. So let me repeat. An element of Hn of x is basically equivalence class, right? And what is this equivalence class? Well, it is denoted by the square bracket x. And what is this x over here? Well, this is an element of kernel of Fn. And what is this square bracket x? Well, the square bracket x is the collection of all those elements in kernel of Fn which are equivalent to x, right? That's how we define this equivalence class. So x prime in kernel of Fn such that x prime is equivalent to x. And how do we define this equivalence relation? We say these two elements are equivalent if x prime minus x belongs to this image of Fn plus 1, right? Now we know that from these properties that we studied above, that if x prime lies in kernel of Fn, then phi n of x prime must lie in the kernel of Gn. Okay, so this is something we sort of studied above. If x prime lies in the kernel of Fn, its image under phi n must lie in the kernel of Gn. Okay, so this is a property that we studied above. And similarly, we studied that if x prime minus x, right, this lies in the image of Fn plus 1, and if you sort of take its find its output under this function phi n, this must also lie in image of Gn plus 1. So these two statements are the two claims, are the consequences of the two claims that we saw above, that x prime in kernel of Fn implies phi n of x prime lies in kernel of Gn, and something lying in the image of Fn plus 1 implies that the output of this input under phi n will also lie in image of Gn plus 1. Right? However, phi n is a vector space homomorphism. In particular, it's a linear map. So you can interpret this phi n of x prime minus x as phi n of x prime minus phi n of x. So this difference lies in image of Gn plus 1. So now what are the implications of this statement over here? So let's try to understand. So the implications are the following. If x and x prime, okay, so these are two elements in kernel of Fn. So kernel of Fn, recall, is a subset of Xn. So let's say there are two elements which are equivalent in kernel of Fn. Then what this story tells us is that phi n of x. So you look at phi n of x under this map phi n, and you look at phi n of x prime. These two will also be equivalent, right? However, this notion of equivalent and this notion of equivalence, this notion of equivalence, what is happening? This notion of equivalence and this notion of equivalence are different. So let me just state that, and we can finish today's class, right? So what is this equivalence relation? So x and x prime, they lie in kernel of Fn, which is a subset of Xn. So when I say x and x prime are equivalent, this is equivalent to saying x prime minus x lies in image of Fn plus 1, right? Similarly, when I say phi n of x and phi n of x prime are equivalent, first note that phi n of x and phi n of x prime, they are elements of kernel of Gn. So when I say these two elements are equivalent, I am saying that phi n of x prime minus phi n of x, okay, this lies in image of Gn plus 1, right? So this is how I define this equivalence notion, right? And one can say that, because of the two claims, this relationship actually holds, that x equivalent to x prime implies that phi n of x is equivalent to phi n of x prime, right? And from this, one can actually see that, let's say you have an equivalence class with regards to x in Xn, right? So the equivalence class of x in Xn is the collection of all those elements x prime in kernel of Fn, such that x prime is related to x. And now we can talk about the equivalence class of phi n of x in Hn of y, right? So this is an element in Hn of x, and this is an element in Hn of y, right? So we can talk about this, and accordingly we can so let's see where I have defined this. Surprisingly, I have not defined it. Okay, so we can now talk about a map. Okay, so recall what was our question. Our question was, what is the relation between Hn of x and Hn of y? In particular, is there an induced map? So my claim is that indeed there is an induced map, and the induced map now takes phi n star of this to phi n so let me be careful. This is the equivalence class associated with x. All right, phi n of x. Okay, so this is the induced map, right? So I think we are at the end of the class. So let me just say one thing and we will conclude, right? So we have some chain maps at the top. We have some chain maps at the bottom. Using these chain maps, we can come up with these homology spaces, right? And one can ask, is there a map that is a vector space homomorphism between this vector space Hn of x and Hn of y? I am claiming that this phi n star is indeed that map. Okay, so this map is defined in the following way. It takes this equivalence class in Hn of x and maps it to the corresponding equivalence class in Hn of y. Okay, so let me pause over here. I think I did not do a good job in explaining this. Maybe when we meet in the next class, I will spend some time in explaining this one more time, and we can see it from there. So let me stop now. Let me stop recording.